Friends, in this video, we are going to revisit problem 2641, cousins in binary tree 2. Here, I regard this problem as a continuation of today's daily challenge problem 2583. So essentially, we can use the traversal in problem 2583 to solve this problem, but the extra step is to reset the value. So with that said, let's look at the problem statement. So here we are given a binary tree, and we want to replace the value of each node in the tree with the sum of all its cousins' values. So here, two nodes of a binary tree are cousins if they have the same depth but with different parents. So here we call cousins, right? Another concept that is related is siblings. So we call siblings as two nodes with same parents, right? So we want to return the root of the modified tree. So if you look at example 1, so in the first three nodes, like 5, 4, 9, so the values are replaced by 0 because 5 have no cousins. Similarly, 4 and 9 have no cousins because 4 and 9 are siblings. So if you look at the last layer, so you have 1, 10, and 7. So the two nodes 1 and 10 have a cousin 7, right? But 1 and 10 are siblings. So we are going to replace the value of 1, 10 by 7. And put it another way, 7 has two cousins, and that is 1 and 10. So we replace the value of 7 to be 11. That is the sum of 1 and 10, right? So that's the main problem statement and one example. So here are some constraints. For example, the tree is not null, and this is a node value, not very essential. So here we are going to use a complementary strategy. So because we can compute the level sums, and then for each node, we just reset its value to be the level sum minus the sibling sum. For example, 1 and 10. Right, for those two nodes. So the sibling sum is 11 and the level sum is 18. So we're going to set those two values as 18 minus 7, minus 11. That will be 7 and 7. Well, for 7, so the sibling is just itself, right? So the level sum is 18. So 18 minus the cousin sum, the sibling sum 7, you get 11. That's why we have 11. So with that said, we are ready to go to the coding. So for the coding part, the first part will be rather straightforward. So first we are going to do a traversal to get the level sums. So this is a very standard. So let's write a function, get level sums. So here we accept a root, and then let's return a dictionary. So the key will be the level index, and the value will be level sum. So basically, we can initialize index. So we can call it original level index. Let's call it let's say 0, right? Then the level, let's do this idx, and the level will be originally contain the root itself. Then we do a while loop, while level. Let's first get the level sum. So the sum, it will be sum of node value for node in level. So I'm going to collect non-null node in each level, right? So this will be the sum. Then what we are going to do is the idx will be the sum. And then we are going to update the level. So we are going to do this. We collect all the children of the current level nodes. So child for node in level, and for child in node left, node right, and if child, right? I guess here the filter using if is important because this way, because we are going to collect node value, we need to access this attribute. If the node is null, so we cannot access this attribute, right? So after we can put this here, update the level and the index correspondingly, right? So we are going to increment the index by 1. Then we are going to return the d. So this is the function. So we can call this function to get the level sums. So let's print out this just to have an idea if our implementation is correct. So for the first example, right, so we get 5, 13, and 18. So level 0, 5, level 1, 13, and level 2, 18. So here I'm using the assumption that root is at level 0, but the index is not essential for this problem, just as long as you use it in a consistent way. So with that said, now we are ready to do the resetting. So actually for the resetting, it's also, there are some details. So we need to avoid to do the subtraction after we reset a node, right? So in this case, what we are going to do, let's see, I'm going to call this one reset the values. So what I'm going to do, I'm going to use say stack. So we have root and the corresponding level. So in other words, we are going to store node and level. So what we are going to do is we do not set the current node value, but we set the children value in the process. So this way it will avoid, you reset after you have already, for example, you reset 4 to be 0, and then you use 13 minus this, you will get, for example, this one. It's more much clear. So if you set 1 to be 7, and then when you do 10, right, then you already set it to be 7, then you compute the cousin sum, that will be 17. Then 18 minus 17, it will be 1, but the value should be 7. This is the 1 point. When you do the traversal, you not directly set the root, the node value we are currently visiting. Rather, you set the children's values. So let's see, while s, we get a node and level. So so level because s pop, right? Then we are going to get the sibling sum, right? So let's also call, let's see, children sum, value sum. So then we are going to check if node left. So in other words, this is the instance we can increment this value by increment node left value. So because we have done this if check, so this expression, in other words, the access to the value attribute is meaningful. So similarly, if node right, so we can do same thing essentially. But here we need to change it to be right. So this way, for the two children, we get the sibling sum, right? So this is the sibling sum for the two children. And then we reset the value for those two children. That's the main point. So let's see. Here we need to still do this. If node left, so what we want to reset is node left value. It should be the level value minus the sibling sum. That is level sums. So because the node is at the current level, so the children will at level +1. Then this one minus the children value sum or the sibling sum. So this is the one. And then what we are going to do, we append, say, node left. So the level is one level deeper. So this is the one. And then we can do the same thing for node right. So node right value. It will be the same thing. But these two values should always be the same if they have both left and right children. So similarly, we append node right level +1. So then we can return the root. But don't forget, actually, we haven't reset the root value yet. So we want to set root value to be 0 because root does not have any cousins. So this is a full solution to this problem. Let's do a quick check. Yeah, it passes the first example. Now let's look at the generic case. It passes all the cases. So here, let me make some comments. So here, if you do left and then you do right, so here the order does not matter. So similarly here, right? But in general, if for traversal, so here order doesn't matter. Same here. Order does not matter. However, if you want to restrict yourself to a certain order traversal, like say post-order traversal and pre-order traversal or in-order traversal, here the way you put left and right is important, right? But for this problem here, so the order does not matter. So with that said, I guess that's basically about it for this problem. What I want to convey is that this basically really the same problem as 2583, but with some resetting. With that said, that's it.